All right, so this little tutorial is going to show folks who are struggling with the parts per notation, how it works and give a few examples. So basically, parts per notation is incredibly easy, but because it's so easy, oftentimes we can't find good YouTube videos about it, and you can't find good resources in your textbook about it, things like that. So let's talk about parts per notation. So the most common form of parts per notation that you're accustomed to is parts per 100. You've never heard of that, guaranteed. Or PPH, no one ever uses that. We use I suppose we would call it a slang term, percent. And so percent is this idea that you take a certain number of parts in 100 other parts, and that's your percent. So for example, for a medical field question, if you have 5 milligrams of insulin and you dissolve it in a total solution of 100 milligrams, then what you've got is a 5% solution. We did the math, 5 divided by 100, it's 0.05. But we learned in like elementary school, right, that you're going to take that decimal and move it over 2 spots for it to be a per 100 or per percent. No one really probably explained to you the reason for that, right? And the reason is that percent sign here means divide by 100. It's per 100. All right. More commonly, we're going to see in science the abbreviation ppms, or parts per million. And so say let's take an environmental chemistry question. If you've got soil that's been contaminated with lead, and it's got 5 milligrams of lead in a million milligrams of soil. Well, what does this mean? Well, this means that you have 5 milligrams of lead in 10 to the 6 milligrams of soil. I far prefer using scientific notation here, right? And that means you've got 5 parts per million of lead in that soil. And so when you get your lead soil sample back, it's going to say a certain number parts per million. It's not going to say you've got 5 milligrams of lead in a million milligrams of soil, because you didn't send them a million milligrams of soil, right? You sent them a little tiny bag, maybe like a 1 cup of soil. Of course, does it get bigger than that or smaller than that, I suppose? Yes, of course. So parts per billion is another common one. This one we might see in environmental chemistry for looking at PCBs, those forever chemicals that are so useful in industrial processes and so bad for human life, for seal life, for whale life, for any higher form of life that has a brain. PCBs get in there and mess with it. And so, but we don't see them in really high concentrations out there in the environment. But because they're forever chemicals, they don't ever really break down. It causes lots of problems as they build up in fat tissues of animals, right? So anyway, side tangent there. But if we're looking at parts per billion, we're talking about 5 milligrams of PCBs in 10 to the 9th milligrams of water, way more water, right, than we were talking about earlier with soil, and that is 5 parts per billion. Now, what if we were going to try to do some math? All right, I've got my recommendation to think of parts per million is just like any other concentration. Just use it as a conversion factor when you're doing these unit conversion math problems. And so let's say we have this hypothetical question. I've got a kilogram of soil. It's got 2 parts per million of lead in it. How many milligrams of soil are in my 1 kilogram bag of soil? Well, you're going to start with what you have over 1. So you have 1 kilogram of soil in the bag. Put that over 1. And you're going to multiply it by conversion factors to change the units till you have the units you want, which is milligrams of lead. And so I'm going to multiply it first by my 2 parts per million conversion factor. That is 2 kilograms of lead in 10 to the 6th kilograms of soil. You'll notice that I kind of just kept the unit of measurement the same, right? So before I was using milligrams as an example, but because they used kilograms here, why not just keep it as kilograms? Keeps it simple, right? And then you're going to multiply that to convert kilograms of lead, which is what you have here. I suppose I should cross my units off, right? So kilograms of soil cancels here. And I'm left with kilograms of lead, right? And so I'm going to multiply by a conversion factor to turn milligrams to kilograms. And this is why metric works so nicely with science, is kilograms of lead cancels. you're left with milligrams of lead, and it just so happens that there's 10 to the 6 milligrams of lead in a kilogram of soil, so you can just divide 10 to the 6th by 10 to the 6th. Those cancel, and you're left with 1 times 2, or 2 milligrams of lead. And so a lot of times we're going to try to always, in science, use the metric system to our advantage to get those units to the correct size. And so if I'd asked for how many kilograms of lead, that would have been a lot more, or a lot fewer kilograms of lead. It would be a really small kind of awkward number, right? 2 times 10 to the negative 6 kilograms lead. But if you turn it to milligrams, you're suddenly removing that awkward number, and you have a very usable number, 2.0, right? This is going to apply in your fluoride questions, right? So if we take a look at the math I did to calculate how much fluoride I would be ingesting if my water had 0.7 parts per million of fluoride in it, 0.7 parts per million being the amount recommended by the American Dental Association and what is added to a lot of municipal water supplies. Then I just have to remember that 0.7 parts per million is the same as 0.7 milligrams of fluoride divided by 10 to the 6th milligrams of water. So if you have a whole lot of water, you've got 0.7 milligrams of fluoride. And in the water treatment plant, right, they're calculating this. Every time 10 to the 6th milligrams of water goes by, they're adding 0.7 milligrams of fluoride to that water. And so I would just use it then in my conversion factor. I start with gallons of water that I drink a day. I drink a ton of water. And no, I don't feel bloated. I feel amazing. I just get lots of exercise and I'm out in the hot sun. This is probably not accurate for my winter water consumption. It's true. And then I'm going to convert this to metric because nothing is worse than gallons when you're doing math. And then I'm going to convert the volume of water to milligrams of water. And then that is going to allow me to multiply by the conversion factor, parts per million, but in this form, right? 0.7 milligrams of fluoride per 10 to the 6 milligrams of water. And that is going to give me my final number of milligrams of fluoride I would ingest per day if my water was fluoridated. So there you have it, parts per million, super easy. Or parts per notation, super easy. And you just got to remember, it's just like any other conversion factor. It's just like, what was the first conversion factor we used was density, which, you know, is a mass per volume conversion. Here we got mass per mass. It's just another way to change the units on your initial starting number to get the units that you want.